Okay, I hope I'm audible to you. So we'll start today's session. So hope you all had a wonderful week. So we'll be compensating for the last week tomorrow. We'll have a session today 6 to 8, and then tomorrow also we'll have a session from 6 to 8. So welcome to week 6 of the problem solving session of natural hazards. So I'll be sharing my screen just a moment. I hope the screen is visible to you. Okay. Okay, thank you. So yeah, so we'll start today's session. Uh, so today we'll be discussing about volcano. So your week 6 has a few discussion slides on volcano, and then you have the landslide. So I thought today I'll discuss focusing on volcano, and then tomorrow we'll do on the landslides. Although your assignment is already done on this part, it's better for a revision. So, what is a volcano? So, like everybody might be familiar with that. So, what do you understand by a volcano? You don't have to be technical, but you can just tell me what is your understanding on that. Okay, so the volcano is basically, uh, we have seen it on TV and we have heard about it. So, it's basically a hill or a mountain which is in the shape of a cone, and it is formed at a vent from which magma reach the earth's surface and it erupts. So the lava, which we call, that is the basically the magma on the surface. So what I'm trying to say is, um, so you have a hill or a mountain like this, uh, from which, like basically what we see on the surface is you have a hill like this, and then when the volcanic eruption occurs, so you have this lava coming out. So what is happening inside? So we, if you remember, you will remember that the volcano and earthquakes gives us an idea about what is happening inside the earth. So they are basically endogenic processes. So what is happening inside is basically uh, you have a vent like this, and then you have a magma chamber beneath. Okay, so so when this lava is inside the earth, that is known as the magma, and when it comes out, you call it as the lava. So in this magma chamber, this molten rock is there, and then when it comes out and erupts, then you call it as the volcanic eruption. So this whatever magma you see, that is basically molten rock. So how does this magma generate? Like how does it form? So magma is molten rock. So how does the rock melt? So for that you need to have a little bit of understanding about this. So it magma can generate because of change in pressure and temperature conditions. So you don't see a rock lying on the earth's surface melting, right? So you are seeing a rock near your house that doesn't melt because the temperature and pressure condition is not sufficient for that particular rock to melt. So, when the pressure decreases, the hot rock can melt. So, if the temperature is also high and pressure is also high, so hot rock may not melt, it can withstand it. But then when the pressure decreases, if the rock is at a higher temperature, it can melt. It's not necessary, but it may melt. Then the melting temperature controls when a rock becomes magma. So that this melting temperature is dependent. So if you know a little bit of what constitutes a rock. So you have several minerals which are constituent of a rock. So each mineral will have a melting temperature. So if that rock is constituting of a majority of a mineral which is melting at, say, like for instance, let's say 900 degrees Celsius. So then that melting temperature is 900 degrees Celsius for that rock, and then that rock will melt and form the magma. So this is a diagram which tells you that. So the melting temperature of a rock depends on its depth within the earth. So if you remember, I might have mentioned it earlier also. So on the surface, we call it as, let's say, a normal temperature and pressure condition. But as you go beneath the earth, pressure also increases, the temperature also increases. So if you take a look at this illustration which is given over here, so they have said that a hot rock deep within the earth, like say a rock above a subduction zone at A. So this is the position of the rock. It may melt as a result of an increase in temperature, a decrease in pressure, or the addition of water that shifts the melting curve to lower temperature. So this is basically a graph which shows an increase in temperature with depth. So this is like as depth increases, okay. So pressure is also increasing. So this is deep crust, this is the earth surface. Then you have the temperature over here. So let's say this is the melting temperature, okay. So this line indicates that below this line, that is below this temperature on this side, that rock will exist as a solid, and if it is above that line, that is above that temperature, it will exist as a melt. So the different parameters that dictate whether that rock is going to melt or not and become a magma is the uh, it can be due to an increase in pressure, an increase in temperature, a decrease in pressure, or the addition of water. So if you know, like sometimes adding water can also decrease the melting point. So it need not go to that much of high temperature. Even at a lower temperature, that particular rock can melt. So these are the conditions. If you can keep it in mind, then that is well and good. So this is how magma generates. So what are the properties of magma? So each magma will have different properties also. It's not that all magma is same. So the first one is viscosity. Viscosity is basically, if you're familiar with it, it is the resistance to flow. So if you say some material is viscous, some liquid is viscous, we say that it is not easily flowing. So let's say you have honey. So honey is viscous, right? But at the same time, if you have a glass of milk, compared to honey, that milk is less viscous. It can flow easily. So if you pour, let's say this is a table, and or rather you consider this as a slope, okay. So on one time you're putting a drop of honey, so the time the honey takes to come down from, say, like this point to this point, and for milk to flow from this point to this point is different, because milk will flow easily, which says that milk is less viscous, and honey is more viscous, so it will take a long time to come down. So that is what viscosity is. So similarly, magma also, like one of the properties of magma is viscosity. There are different kinds of magma. So there can be more viscous magma, and there can be less viscous magma. So as I said, it is the resistance to flow. It mainly depends on the composition and also on the temperature. So composition is a huge factor, and then also the temperature. So if you have higher silica percentage, silica is basically what? SiO2. Okay. So if you have high silica percentage, then the magma will be more viscous. So silica is high means viscosity is high. So if we take a look at this, these are different rock types. So this is basalt, this is andesite, and this is rhyolite. So this is a volcanic rock, and then this is a plutonic rock. In terms of geology, we call it like that. That is basically when the silica percent is increasing. So this basalt you mostly see in this ocean floors and all. There you don't have much silica percent, that is basalt. and then as you go come up, then it becomes to like it comes to rhyolite. So that is like increasing silica percent. So we can say that a rhyolitic magma will be more viscous compared to a basaltic magma. So basaltic magma can flow easily when compared to a rhyolitic magma. So viscosity is the first property that you have to bear in mind, property of a magma. Why I'm discussing the properties of magma is because you have to understand not all volcanic eruptions are same. Like you might see a news on the TV that this volcano erupted or this one erupted. So, but then they are not very similar. Like different, the volcanic eruptions are also different in nature. The other one property is the volatiles. Okay, so the volatiles is basically whatever gases or is present inside that magma. So if the dissolved gas content is high, like mostly you have water vapor and carbon dioxide. So if you remember, I don't know if I put the diagram over here. Okay. So let's say this is a subduction zone. So I hope you are now familiar with the term subduction. So this is the ocean floor going down, oceanic crust, and then you have the continental crust over here. So when the oceanic crust is going down, it is also taking some water with it, right? But when that water reaches in this depth, it is at a higher temperature, so it can release water vapor. And at the same time, some amount of carbon dioxide might also be present in within the rocks, like say some carbonate rock is present, so carbon dioxide can come out. So most abundant volatiles found in the magma are water vapor and carbon dioxide. They are not the only ones, but they are the most abundant. So the depending on the volatiles present, also the magma eruption can vary. So if the water content is high, like the water vapor content is high, that volcano eruption will be very violent in nature. So if the water content is really high, that is the one most of the time you see the volcano eruption videos, like with that huge sound and all. That eruption is happening because that volcano, that magma contains higher water content. That is why, or higher volatile content, which is why you have a violent volcanic eruption. If you have any doubt, please stop me, or if I'm going a bit fast also, you can ask me to slow down. Okay, I'm just, because these subduction and all those things I have explained earlier, so like I hope you are understanding when I'm using such terms. Even if you don't understand, you can just stop me and ask me. Okay, so as pressure decreases, solubility also decreases. Solubility is the ability to dissolve, and the gases will bubble out. So the thing is, when the magma is coming out, okay, so the magma is within the chamber. Let's say this is the uh, uh, magma hill, or the volcanic mountain. So this, here you have the magma chamber deep inside the earth. Okay, so you have a lot of magma here, and this magma has a high volatile content. Volatile content, so it will have high water vapor and carbon dioxide, which are most abundant, and then other volatiles will also be present. For the time being, we are focusing on the water vapor, let's say. So when it is in the magma chamber, it is at a higher pressure and higher temperature condition, right? So it is very hot, and it is at a higher pressure condition. So all whatever water is present, it is dissolved within this magma. So it is not going to come out. But as this magma is going to rise through the vent, that is, as it comes towards the surface, the pressure is going to decrease. Okay, the pressure which was holding this magma, the water vapor, like all the volatiles together, that is decreasing. So when that decreases, the solubility, that is the ability to dissolve these volatiles, that will also decrease. And as a result, what will happen is whatever volatiles is present, that will become bubbles. So it will bubble out. So instead of staying within the magma, dissolved within the magma, whatever volatile is present, that will bubble out. So as a result, what happens is that when the magma erupts, okay, when this volcano erupts, these bubbles will be causing a violent eruption. Like the presence of these bubbles will cause a violent eruption. So when the water content is less, you will have a quiet eruption that is not very loud. Like you can see magma or lava coming out, but then it's not so loud. But if you know, most of the time when you look for volcanic eruption videos on YouTube or anywhere, you might be seeing those ones which are explosive eruption, and that is because of the higher water content. Those eruptions which do not have that much of water content, that will be very quiet in nature. So this image is basically telling you what I just explained with this. So if you see, okay, they have put the arrows like this. So what I'll do is, at this point you have a higher pressure, and as you come out the pressure is less. Okay, so if you look at this, at this point you have few steam bubbles, not much, but very few. But as you go towards the surface, the pressure is decreasing and the amount of steam bubbles is increasing. So here we have few steam bubbles, and then as you go up you have numerous steam bubbles, and then that will result in the violent eruption of that volcano. So the first property, if you remember, was the viscosity, and then you have the volatiles. Then comes the volume. So volume of magma in a single eruption. So that is also another factor. So how much volume of magma is present in the magma chamber, and how much magma is erupting during a single eruption. That is also dictates what kind of eruption is happening. So uh, if you remember, I had shown you a world map during the time we were discussing the earthquake also. So I had shown you the tectonic environments where you normally find such volcanic eruptions or earthquakes. So can anyone tell me where do you find such things very frequently? You can make a guess, or if you remember, you can just tell me. This is just to refresh your memory. I'm not going to grade you or anything, just to refresh so that it will be helpful for your exam also, which is coming soon. Where do you find tectonically active sites if you look at the in terms of let's say plate tectonics? There is a particular term which I had explained in the previous sessions also. So just try to recollect. Not exactly. Like I understood what you're trying to say. Fault, not just fault line. It is like plate boundaries. Okay. So tectonically active regions. So it is along the plate boundaries. So I have a map in the upcoming slide, I think. So I can show you there. So it is along the plate boundaries where either you have the spreading boundaries where two plates are moving away from each other, or you have subduction zones where two plates are coming towards each other. So these are the primary regions where you find uh, such volcanic mountains and volcanic eruptions frequently happening. Not just this, I have another example also, but most of the time this is the location. Then you have hotspots. That's what I was saying. So not just plate boundaries, you can also have volcanic eruptions or volcanic mountains in hotspots. So I'll explain that in detail. I had explained it once before, but we'll go through it once again. Then the nature of eruption. So peaceful zones, peaceful eruptions you find mostly in the spreading zones. So in spreading zones, I had said, right, how the ocean floor generates. So let's say you have, okay, just a moment. Okay, so let's say this is a spreading zone. So here, this plate is moving in this direction, this plate is moving in this direction. So a gap is being generated over here. So the magma will come up through this opening, and it will just come out, and then it will solidify. That is how your ocean floor is forming. A basaltic magma is coming out. So that is how it is forming, and this is very peaceful. It's just going to flow out, and nothing much, no, not many sound or anything. It's just going to flow out, that's it. However, in subduction zones, if you remember, uh, you have this subduction happening over here. This is the oceanic crust, and then you have the continental crust over here. Okay, just a moment. Let me see. Now you can see. I hope it's visible now. I had made it to the large screen. Can you see that? Okay, just a moment. I think this slide is not changing when I'm changing it. I'll just stop sharing once and then I'll share it again. Okay, you can see this map, no? Okay, thank you. So this is what I was talking about. So you have these plate boundaries, okay? So so as I was saying, so you have a subduction zone. So one plate is going down, it is subducting, and then okay, what I'm drawing is not coming, I think. Okay, I'm not making it as a big screen because it's not coming properly. So I'll show it over here itself. Okay, now it's coming. Okay, so this is a subduction zone, and what I was just trying to tell you is, if you have a mid-oceanic ridge where the magma is flowing out and it is not very violent, but in subduction zone, what happens is, you have this material coming down. So this, as I said, some water is also coming down, and when the rock melts, that along with the volatiles is coming up, and you have volcanoes over here. We call it as these as volcanic arcs or continental arcs or island arcs. You have a lot of volcanic mountains along that subduction zone. So this, the reason why this is very quiet and like peaceful, and this is violent, is because in this one, that volatile incorporation is less in the case of spreading zones. But where you have these subduction zones, volatile is also getting in into that magma. As a result, you have a chance of more violent eruptions. So this is basically the ring of fire. So Like you might have heard about it. So this is because all these regions surrounding that, all these are subduction zones. I should have included the previous map so it would have been easier for you. But essentially, whatever these red arrows, these lines are showing, they are subduction zones. So along this region in the Pacific, ocean, you have a series of volcanoes present. So that is why we call it as the Ring of Fire. So here I have a video just to, you know, give you a visual representation of what I've been telling you. I hope you are able to hear it. Okay, so I hope that gives you an understanding of what I've been explaining. I'll just once more try to show it in this slideshow mode, but I'm not sure if it's coming. it's not coming in your screen, so we'll go with the this mode only. Okay, so as you have seen in the video, and as I have also mentioned, so we have these spreading zones, or where you have the divergent plate boundaries. So in such spreading zones, the lava which is coming out is basically basaltic lava. Okay, so if you remember, basaltic lava is those which have very less silica content. Okay, SiO2 content is very less in basaltic lava, and therefore they are less viscous, or they flow easily. So it is not much hazardous to humans except in Iceland, where you have this spreading zone visible on the surface rather than beneath the ocean. So that example in Iceland is the mid-Atlantic ridge. So normally the spreading zones are inside the ocean floor. You don't see it on the surface, but the only exception is in Iceland, where you can see the ridge formed as a result of spreading on the surface. So here the divergent boundary is between. I'll just So here it is between the North American plate and the Eurasian plates. So it extends into the South Atlantic Ocean between the South American and the African plates. So then it extends into the South Atlantic Ocean. So this is the mid Atlantic ridge. So it's a very it's something that you can keep in mind because it's an exception. Then comes the subduction zones. So subduction zones host the most hazardous volcanoes. So here, if you remember, as I said, you have the basaltic magma to the rhyolitic magma to the andesitic magma. So that kind of change is happening because the magma is coming from the deep part of the earth to the crust, through the crust. So an example is the Cascade Range of Western North America. So you have a series of volcanoes like this. Okay, these are all. So basically, what is happening if you take a cross section of this? So what is happening is this water region that you're seeing. So that's going beneath this region, and then as a result, so what I'm showing or what I'm drawing is just a two-dimensional image. So what you have to understand is that this is basically in a three-dimensional form. You have to imagine this. So you have volcanic mountains along this arc. So that is how you have a series of volcanoes present. I hope this is clear to you. If not, please ask me. So the position of volcanoes farther inland, if the inclination of slab is gentler, so that is basically if the slab is going down in a gentle fashion, so it will be more in this region, and if it is subducting at a higher angle, so it will be closer to this trench area. Okay, that is what they're saying. So farther inland if inclination of slab is gentler, and closer to trench if the inclination of slab is steeper. So magmas generally contain some water, which results in the violent eruptions which I was talking to you about. Then comes the hotspots. So they are an exception. So most of the time we say volcanoes are found in the plate boundaries, but hotspots are an exception. So they are generally, it's an area of the earth's mantle from which hot plumes rise upward, forming volcanoes on the overlying crust. So this is not formed at the plate boundary, rather let's say this is the crust, and then you have the mantle somewhere over here. So from deep within the mantle, this hot magma is coming out, and then it is forming the volcanoes. So here there is no spreading or no subduction going on, but rather the volcano is coming from deep within the mantle, and it comes out through the overlying crust. So these are fewer in number. They are not as abundant as the other kind of magmas, but they will produce a large amount of or large volume of magma. They do not have that much of water present compared to the other two, but maybe they can have, but not very significant. So therefore you have a quiet eruption in these hotspot regions. The example is the Hawaiian emperor chain of volcanoes. So this is a Hawaiian emperor seamount chain. So if you know, you like, you might have heard about Hawaiian islands, right? They are really good tourist spots, but on a geological aspect, Hawaiian islands are important because of this volcanic mountains present. So here I had shown this image earlier also. So if you see, what essentially is happening is you have this mantle plume, or this is where you have the magma, and this is your plate. Okay, so in this example, this is the Pacific plate. So first you had this magma which formed over here. So this hot spot will never move, rather the plate is going to move. So the plate is moving in this direction. So hot spot is intact. So this volcanic mountain, it will come over here, and a new volcanic mountain is generated here. So similarly, as the plate move in this direction, the older ones are going to go away, and the newer ones are going to, or the younger ones are going to be like this, closer to the mantle plume. So that is what is shown over here. So here if you see the Hawaii, right now it is the active one. Then just before that you have the Oahu. Then you have the Midway. So if you look at the age, this is like in millions of years. So 2 to 3 million years over here. Then 25 million years, 43 million years, 60 million years. So the plate motion, or the Pacific plate, is moving in this direction. So in that terms, if you see, this was the one which formed first, and this is the youngest one, which is currently active. The other ones have almost become inactive, and they have turned into seamounts and all. Seamounts is basically when that tip of that mountain is eroded, and then you have a flat surface kind of thing. Like it's no longer going to generate any kind of magma or anything. So this is a cross section of that. So you have the Hawaii, Mauna Loa, Kilauea. All these are currently, whenever they talk about a eruption in Hawaii, this Kilauea, all these things are talked about. And these Maui, Molokai, Oahu, Nihuakoi, all these are older ones. So as you go away from the mantle plume, they become older. So I hope you understand that. So this is an exception. Most of the volcanic eruptions or volcanic mountains are found along the plate boundaries, but an exception to that is the hotspots. This So we have so far discussed about how, what kind of volcanoes are present, what kind of eruptions are there. So when does these become volcanic hazards? So if you remember from the first session, I had told you, right, all these are natural events, they keep happening throughout the earth's history. So they become hazards when they're posing a threat to people's life and people's like life and property, not just people, like any kind of animals or anything. So volcanic eruptions have been happening throughout Earth's history, but they became hazards when they posed a threat to life and property. So, volcanic activity, a positive side is that it gives an area rich and fertile soil, which is ideal for agriculture, because that volcanic material is like very mineral rich. So, as a result, it is ideal for agriculture. Landscapes of soaring, majestic mountain peaks make desirable spots for homes. So, like such big mountains and all those things. So, people find it very attractive. To tourists go there, they build homes or stay, like for staycation, they can go. So, all those things. So, because of these reasons, because of the fertility of that soil and because of the beautiful landscape, dense population are found in shadow of active volcanoes around the world. So because of this reason. So if you remember, I had said, right, that in rivers, people mostly, you can find population along the banks of rivers. Why? Because the floodplains are fertile. So the problem with that is that although they are looking to stay in that region because of the possibility of creating, planting and then developing an agricultural land, the problem is that when severe rainfall or something happens, and then when flooding occurs, they will be the first people to be affected. Similarly, in people staying in the shadow of active volcanoes, they will be affected. However, we can still find. So there are certain situations which are inevitable, right? You don't have any other place to stay, so you have to stay there. So like that. So the lava flows, they're incredibly destructive to anything in their way. So you can imagine, right? That is like burning molten magma is coming. So it's very hot, it is at a higher temperature. So it is going to destruct anything which is on its way. It generally pose little threat to human life because they move so slow and cover small area. But that is not or in all the cases. Okay, so those magma which or lava which flows very quickly, rather those ones like basaltic lava, they are a bit more quick. So it's not a general thing, but then largely you will have enough time to move away from the lava, like oncoming lava. Basaltic lava flows, being less viscous, can travel up to 25 kilometers from the vent. So, vent is basically from where that eruption happened. So, basaltic lava flows are less viscous. Less viscous means they can easily flow. So, they will flow to almost like 25 kilometers from that vent. However, andesitic lava flows, which have more silica content and which is more viscous, compared to the basaltic lava flows, they will only cover a smaller distance from the central vent or the volcanic vent. But in some cases, there are exceptions always. So, in some cases, like the Vesuvius eruption in 1805, they have seen that such lava has flown rapidly in some cases. So, it's not always a very general condition, but mostly this is how it happens. Basaltic lava flows, they come in two major forms based on this viscosity which we were discussing. Okay. So the basaltic lava flows can either be Paho Iho and Aa lava. So this name is mostly attributed to this Hawaiian region. That's why such names which is not very familiar to us is shown. So Paho Iho is the lava flows with smooth, billowy or ropey surfaces. So its surface mostly will be very smooth, ropey kind of thing. Okay, so we call it kind of like this. It's very texture is very smooth on the surface. However, Aa lava is the lava flow with rough, jagged or clinkery surface. So Aa lava will be those which has this pointy edges will be present, like it will break. So Paho Iho forms in less viscous lavas relative to ones that form Aa. So basically, these volcanologists or even people who visit such sites, they are prone to getting hurt in lava flows compared to the Pahoiho. Pahoiho is more smooth in texture, so you can like go through it very easily without getting hurt much. But in lava, they are very blocky kind of structures. They have pointed parts, like it is broken, so because of that there is a tendency for you to get hurt. So this is a video showing how these are generated. So so you can see the ropey texture also over here. The main classification is the Pahoihoi and the lava. But when this volcanic eruption is happening within, like beneath or on the ocean floor, so then whatever structure that is formed as a result of that, we call it as pillow lavas, because they look like fluffed pillows. If you had seen the video. So I hope the classification is clear to you. Now we'll go to the next slide. So here there are several flows. Like we have these like lava flow, we have the pyroclastic flows. So pyroclastic flows are those where you have a mixture of volcanic ash and steam that pours down the slope as it is too dense to rise. So what happens is when the lava is coming out, so along with that the lava will also have this volcanic ash will be there and steam will be there, which cannot go to that much height, so it will come down. So that we call it as the pyroclastic flow, and it has a because of its constituents, like it is ash and steam, so it has a speed of 50 to more than 200 km per hour. So in this image itself you can see, right, how dense it is. It will create a lot of problem with visibility, so like when airplanes are going or anything. So this like if an eruption happens and pyroclastic flow is so dense, then airplanes are advised not to pass through that, because the visibility will be so less that they will not be able to come out. And here you can see a truck is there, and then the pyroclastic flow is coming. So it flow that is very fast when compared to the lava flow. So I think this is a video showing the pyroclastic flow. So yeah. So you can see how quickly they are coming. See how quickly it is moving. So that is basically giving you an idea regarding what pyroclastic flow is and how like destructive it is. So like mostly whenever we talk about volcanic eruptions, we associate it with the lava which is coming out. But this pyroclastic flow, because of the speed with which it can engulf the surrounding areas, so that is even more dangerous. It can cause respiratory problems. It can burn the materials on its path. So all in all, it is very dangerous. So whenever that's what they were saying, like you may see, like you have a mountain, volcanic mountain which has not erupted for a long period of time. That doesn't mean that that mountain is not capable of a proper eruption, but rather it may cause a very destructive eruption when it will, it is ready to erupt. So that kind of issues. Same is the case in when we were discussing earthquake also. So just because a fault region has not experienced an earthquake for a long period of time doesn't mean that that is not prone to earthquake. Rather, you must expect a very high magnitude earthquake. Similarly, in case of volcano also. So if a volcanic mountain has been very quiet for a long period of time, that doesn't mean that that is not going to erupt. It will erupt in the coming future. So volcanologists keep monitoring such locations in order to predict and generate a forecast regarding the eruption, and then alert people regarding that. So the volcanic ash, which we were talking in case of this pyroclastic flow, so it's a mixture of rock, mineral and glass particles expelled from the volcano during a volcanic eruption. So volcanic ash is basically all these fragments together. Mixture of rock, mineral and glass particles expelled from a volcano during a volcanic eruption. It is less than 2 millimeter uh, in diameter. So diameter is very less. 2 millimeter, you can imagine how small it is. But part of that dark ash column that rises above a volcano when it erupts. So the one that you see during a volcanic eruption, not the glowy part, but the darker one. It can travel long distances and it is carried by winds. Wind can carry easily because the particle is very small, and it is very hard, and it has usually jagged edges. Jagged means pointy edges. So this can cause eye, nose and lung irritation as well as breathing problems. So people who have respiratory diseases like asthma or something related to breathing problems, so if they happen to inhale this volcanic ash, that will be a problem for them, like that can create this respiratory illness for them. So a thick layer of ash may cause roofs to collapse, contaminate water supplies, etc. So it's although they are very small in size, like each particle, but when they come together, that thick layer of ash can cause the roof of houses to collapse. When they accumulate, that roof cannot tolerate that much of weight, so it will collapse. Ash can linger for several years in the upper atmosphere and block sun's radiation, resulting in cooling. That is also not good. Okay. So the example is Tambora volcano in Indonesia in 1815. That was a year without a summer because of this volcanic eruption and the subsequent volcanic ash which was present. So when the ash is creating a barrier, so the sun's radiation will not be able to pass through. So as a result, that warmth and that basically the presence of sun is almost negligent, and it will feel like a year without a summer. This will pose problem for transportation. Jet engines can freeze and stop when they enter an ash cloud. That is why uh, during a volcanic eruption, this aeroplanes or jets are not allowed to go through because the engines can fail. There has been an event like this. I don't remember exactly which one, but so, uh, airplane, just because it had like one of its engines failed, and just because the second engine was functioning, it could go through. Otherwise that entire airplane might have collapsed. So this is an example of the ash accumulation. So you can see over here, this is the roof which is accumulated by the ash and it will collapse. Here is the volcano. So ash from Mount Pinatubo in Philippines collapsed many roofs. Heavy ash from Rabaul caldera in September 1994 collapsed the roof on the left and thickly coated the roof on the right. So this is how that weight cannot be tolerated by the roofs. Then Another thing is the volcanic mud flows. So that will form when ash will combine with the water. So it will pour down with high speeds with a consistency like very wet concrete. So wet concrete you might have seen. So the volcanic mud flow will be similar to that. So it will gather rocks of all sizes and carry it along. And people are killed by boulders in fast moving flows. So we call these as lahars also. Okay. Lahars are formed when that snow-capped volcanic mountains, that snow will melt because of the eruption, and when it comes down with all that mud and everything, so we call it as lahars. So here you can see the mud lines high on tree trunks show the depth of Tutul River mud flow on May 18, 1980. So here you can see the person in yellow. So here you have a person in yellow. On the right is almost 6 feet tall. So this person is 6 feet tall, and this is the mud line. So you can imagine how, that is the scale. So compared to him, this is almost like 12 feet maybe. So that much thick mud flow can come as a result of volcanic eruption. So this this is an example once again. So this is in 1995. So this is a farmland. Not many people have occupied this area, and you have the Mount Rainier over here. So that is heavily clogged with snow and ice. So you can imagine when an eruption happens, so lahar flows are definitely going to happen. So what happens is because you know mud flows are very fast and they can come down very quickly, they can definitely engulf this entire region. But since if you remember from the previous slide, as I said, these regions, because of past such flows, they have become really fertile. So as a result, people have started to live in that area. So in 1995 it was not very accumulated, but in 2009 you can see. However, they are very much risk present in the risk prone area, because this is the mud flow path down valley. So whenever this is going to erupt, the mud flow can definitely engulf this region. So this is something which people should have taken into consideration while developing that area. Another volcanic hazard is the poisonous gases during the volcanic eruption. So, even in the absence of an eruption, gases emitted by volcanoes can pose a hazard. So, sometimes you can only see the gas coming out, not the volcan, that lava. But that gas is very hazardous in nature. So, as magma rises, these gases will come out of the solution because the pressure is decreasing. So it will react with sunlight, moisture and oxygen to produce aerosols. So high concentration of carbon dioxide can be deadly, and it can result in suffocation. So such poisonous gases will be present when the volcano is active, and as a consequence it can result in deterioration of health. So this is a example. This is Lake Neos. It is a water-filled volcanic crater. So volcanic crater is basically, at times what happens is this pointy part is there, no? So that will collapse, and it will become like this. So this later water will fill, so it becomes a lake. So this is a crater lake. So Lake Neos is somewhat like that. So the carbon dioxide in Lake Neos, a water-filled volcanic crater in Cameroon, it suddenly bubbled out and flowed down slope. So it came down slope and over a waterfall just beyond the right side of the photo. So here there is a waterfall. So it came out, and what happened is along its path, it suffocated both cattle and humans. So several cattle died as a result of this carbon dioxide rich water flowing down. So such risk cast, like, most of the time when people think about volcanic eruption, the only image that comes to their mind is the lava. But that is not the only risk posed by the volcanic eruption. Rather, you have several other ones, so like the poisonous gases coming out, the volcanic ash, the mud flows, lahars. All these are problems associated with the volcanic eruption. Another gas, which is the sulfur dioxide, it has a choking effect and it can be harmful to animals and extremely poisonous to plants. So that is another problem. Sulfur dioxide reacts with oxygen in the atmosphere. It will become sulfur trioxide, which reacts with water to form sulfuric acid. So like those with science background, you know how harmful sulfuric acid is, right? So the sulfur dioxide gas, it will react with oxygen, forming sulfur. You don't need the science, like the chemistry that much, but you have to understand that like carbon dioxide and water vapor, sulfur dioxide gas is also present, and that can eventually result in this acid rainfall and all those things. So it can partially block sunlight and it can cool the climate, like I just mentioned. So, can we predict volcanic eruptions? So, just like how I was talking about this in the earthquake session, so scientists can provide long term forecast. So, they cannot say like around this time, like this exactly, they cannot say, but they can tell you in terms of long term forecast. So, once activity starts, they can often warn of an impending eruption. So, volcanologists, they know, so they have certain signs, they keep monitoring the volcano. So if they see that it has started to become active, so they'll make a long term forecast and they'll say that around this time you can expect an eruption, so you have to be prepared accordingly. Another one is paleovolcanology, like paleosismology. So paleovolcanology, what they do is they'll interpret deposits from the past volcanic eruptions and they will create a record how frequently that eruption was happening. So accordingly, they can tell that, let's say, the eruptions were happening between 10-year gap. So 10-year gap has happened. So that trend there, if they can find, then they can say that within the next few years, like on the 10-year gap, another eruption is going to happen. So prediction is basically dependent on the past eruptions and then the activity of the volcano at present, all those things. Intervals between eruptions can be very long, so you can it can even be as long as like 20-30 years. So a volcano that has not erupted in say 1,000 years, it may still be active. So it's not that just because that volcano has not erupted for 1,000 years, you can like flat out say that it is not active. It can be active. Volcanic precursors, just like the in case of earthquake we had four shocks, so like that in case of volcanic eruption, you can have volcanic precursors. So like earthquake tremors can happen, change in level or tilt of the ground surface, changes in gas concentrations, etc. So the scientist or people who study volcanoes, they will monitor all these things, and if they see that frequently some earthquake tremors are happening, or the tilt of the surface has changed, or some gas concentration has increased, that is all sign that and there is an impending volcanic eruption. So this is an example regarding that. So what they will do, most of the volcanologists, what they will do is they will keep this tilt meter. Okay, so when rising magma gets close enough to the surface, it will sometimes push overlying rocks to create a bulge in the flank of a volcano. So a tilt meter measures the changing increase in slope, and then accordingly the people can understand. So this is pre-eruption, so there is no bulge. Okay, so they kept the tilt meter over here or, along the slope. Then magma started rising, so the flank started bulging. So what happens, the tilt meter will move, so the slope has increased. So based on this change, they will notice year wise they are seeing, this is the in how much slope variation is there. So you can see when the eruptions are happening, that slope is high, and when you don't have that much of eruption, which is indicated by the blue lines, uh, it is not very significant. So tilt meter is a good way by which people can study the volcanoes, like impending volcanic eruption. So this is a small video regarding the Pompeii volcanic eruption. So some of you might already know, but it is worth knowing when you are always learning about volcanic eruptions. It is a very significant volcanic eruption in the uh, past which has happened. So you can just watch it. So Pompeii was a city in Italy, and this mountain that you see, that is the Mount Vesuvius. Okay, so that is a volcanic mountain. So this was in that mountain was inactive for centuries. So like for a human being, we can say that an average age not more than 100 years we will consider, right? So in their lifetime, most of them have not seen this volcano erupt, because of which people never expected that this is a volcanic mountain or that it is going to erupt. They never expected such a event to take place. So you can see the pyroclastic material also. So this is a violent eruption. See how quickly it is moving. So this entire city was wiped out because of this eruption. So like that's what, if you have listened carefully, so in a span of 24 hours a day, the entire city was wiped out. Nobody even knew what was happening. So it is said that when archaeologists found this site, this Pompeii city, so they could see this people well preserved in this volcanic ash. That is what they are showing over here, in the position that they were present. Like people, some people were sitting, some people were lying down, some trying to escape. So in that particular state, the volcanic ash engulfed them, and that way they were kind of that preserved. So when archaeologists found the site in like almost 1500 years later, uh, that entire city was preserved in that day. That way you can say, not like how it was before, but that day of eruption, how it was, you know, present. That in that form, archaeologists retrieved this city. So that was just to give you a small understanding of volcanoes and volcanic eruptions. So today the theoretical part is done. Now we'll move on to the problems. Few problems are there. So yeah, I don't know why the slideshow mode is not working properly, but I'll rectify it by tomorrow. So for those of you who are not there, we'll have a session from 6 to 8 tomorrow also, because we couldn't meet last week. So yeah, we'll discuss landslides tomorrow. The answer is already here. One second, I'll just. I don't know why that is not working. Okay, anyway. So the major volcanoes are along the dash, spewing lava intermittently on the Earth's surface. This I had already shown, the ring of fire, the Pacific ring of fire. I'll just stop sharing and I'll share once again and see. I don't know why this is happening. In the meantime, if you have any questions, you can ask me also, for those of you who joined late. Can you see this in the slideshow mode? Can anyone tell me, like, if you can, if it is visible in the slideshow mode or just the slides are visible? Okay, it's not in the slideshow mode. I don't know what is happening. Okay, then we'll continue with the problems. Okay, so the major volcanoes are along the dash, spewing lava intermittently on the Earth's surface. So anyway, since the answer is here, I don't think the options are relevant. So it's just the Pacific Rim. So I have a slide which is showing that image. I'll just, yeah. So this is the Pacific Rim. So you have the Ring of Fire. For those of you who haven't heard, so this is the Ring of Fire. So here you have these uh, these are subduction zones. Okay, so these red lines are subduction zones. So these yellow ones are all volcanoes. So it's basically like a ring. So that's why it is known as the Pacific Ring of Fire. That's why it is known as the Pacific Rim, where you have spewing lava intermittently on the Earth's surface. Mount St. Helen erupted on May 18, 1980, accompanied by an earthquake having a magnitude of. Uh, I don't know, like if it had worked in that slideshow manner, I could have shown you properly. Now all the answers are visible. So this is, I think, from one of your assignments only or past assignment. So you can just, if it was not there in your assignment, you can just note it down. Maybe possibly for your exam, it might be relevant. So my Mount St. Helen, it erupted on May 18, 1980. It was accompanied by an earthquake, which, so you can imagine, right? 5.2 is a significant magnitude when it comes to, when you talk about an earthquake, and an eruption along with an earthquake is not a very good situation to be in. Can you see the screen? I think it went off. Okay, I'm continuing with the slides, but if it's not moving or if you're not able to see, just stop me, okay? So, the eruption of Mount Krakatoa in 1883 was the deadliest event which resulted in dash degree Celsius drop of temperature worldwide at that time. So, if you remember, as I said, when volcanoes erupt, so they send out a lot of these ashes and pyroclastic material into the atmosphere. So, what happens is it will block the sun's radiation coming to the earth's surface. So, when it blocks such radiation coming, so what happens is it will kind of create a cooling effect. So as a result, temperature will come down. So in terms of this, you might just think that okay, it's just 1 degree Celsius drop, but 1 degree itself is a very significant drop when it happens in a global scale. So that is why this particular eruption is important, Mount Krakatoa in 1883, because that resulted in a drop of 1 degree Celsius temperature. The dash were formed near the end of Cretaceous period, which is like 65 million years ago, due to volcanic activity when the Indian continent started drifting from the main Gondwana land. So for those of you, like if any of you are from Maharashtra area, so you might have seen this region, Deccan Traps. So that is basically, if you remember, the Indian subcontinent, it was earlier uh, present in the southern hemisphere, right? So it was over here and then it moved to its position where it is right now. So while it was moving, it is hypothesized, it's not very much like people have not established it for that matter, but it is said that while it was coming towards the position that is present right now, like in 65 million years, what happened is it passed over the reunion hotspot. Okay, so that's a hotspot or a mantle plume was there, and when this region moved through that area, so some amount of volcanic activity happened. So this is known as the flood basalt, like basaltic magma came out and thus forming the Deccan Traps in 65 million years ago. So that's a significant volcanic feature that you can see in the Indian subcontinent. Which volcano destroyed Pompeii and killed 16,000 people? So, as I had shown you the video, that is Mount Vesuvius. This I had asked you in the previous class also. So, the mud flow caused by volcanic eruption onto the Earth's surface is termed as. You're able to see the presentation, right? Oh, okay, okay, हाँ ठीक है. So the mud flow, which is caused by volcanic eruption onto the Earth's surface, is termed as lahars. And you know what lahars are, right? So for those of you who has not been when I was explaining this, so it's basically you have these volcanic mountains which are snow capped. Okay, so you have snow over here. So when the eruption happens, so the snow will melt, and along with that volcanic ash and other material, it will flow down. So that flow is known as the lahars. The Coulomb Terzaki equation. So this is from your assignment only. So I just wanted to recap it. So the Coulomb Terzaki equation, which explained the dash of the material lying on the slip plane, that is uh, shear strength. I think in your assignment solutions, they have given you the explanations for each of the answers. So that's why I'm not going into much detail. But if you want me to explain anything, then you can ask me. So the volcano which exists in India is on Barren Island, which comes in the dash zone. So I'm sorry, like the presentation mode is not working, which is why you have all the answers shown as like this. So it is the Andaman Sumatra subduction zone. So basically, although it is away from the Indian subcontinent, it is part of India, right? So there you have a volcano present. Within the Indian subcontinent, as of now, we don't have any active volcanoes present. So the one which is present is in the Barren Island along the Andaman Sumatra subduction zone. So that's a very possible question that can come in your exam also. Like I'm not saying it will definitely come, but then this is an exception. So this is something you have to keep in mind. That where you have a volcano in India, that is the Barren Island along the Andaman Sumatra subduction zone. So, which one of the following observations may indicate a forthcoming volcanic eruption? So, as I said, when these volcanologists, when they study the volcanoes, so what they look at is the bulging, which I had explained in the previous slide also. So, you have a volcano over here. If it is starting to become active, what happens is it will experience some kind of bulging along the slope. So if the people they keep a tilt meter, accordingly they can understand how much variation is there, and if some variation is present, then they can expect a volcano in the near future. Another thing is the microseismicity. So because such a huge magma chamber is becoming active, so along this area small earthquakes can happen. So if you have a volcano nearby and if you are experiencing small tremors like very frequently at a period of time, then you must expect that that volcano is becoming active and that you can expect a eruption in the near future. Another one is the increase in avalanche felled rocks. So uh, maybe on the slopes you can see this rock material and all. So that can be an indication that the volcano is becoming active. So all these three are those observations which indicate forthcoming volcanic eruption. So if you have a descriptive kind of question in which they say ask you what are the uh, indications of forthcoming volcanic eruption, so you can give these three for that answer. The dash boundary is regarded as the greatest mass extinction of all time, as 96% of all life on earth perishes. That is the Permian Triassic. So those of you who are familiar with the geological time scale, so this is the Permian Triassic period. Overall, as of now, the earth has witnessed five major mass extinction events, but significant life loss was during this Permian Triassic boundary. So that's why this is important. So that way, whenever you're going through the problems or material in your lectures, you just try to go through it in such a way that frame a question out of that material, so that you can understand, like if a similar question comes in your exam, so you can answer accordingly. So this brings me to the end of today's lecture. But then, if you have any question, please feel free to ask, because many of you joined late. So if you want me to explain any particular thing, like you just feel free to ask me. I think we have three more sessions, and then it will be done. So anybody has any question? regarding this volcano or previous classes, anything? We'll have a recap session also. I think it is on March 19th. I don't remember the date exactly, but we'll have a recap session in which I'll just summarize all the things we have discussed till now. Maybe I'll try to include a lot of problems which will be helpful for you in the examination. So, any further questions you have? Especially the people who came in late, like if you have any, because I had today I have exclusively discussed the volcano part. I have not included the landslides. That we'll discuss tomorrow. So any question from your lectures or from this topic anywhere? Yeah. Okay. Huh. No. Pacific, no. If you look at this diagram, can you see this that map? Okay. So, the Pacific Ring of Fire is mainly like these red arrows you can see, no? This red lines. Yeah, these are all subduction regions. Okay. So, subduction is where you have this plates coming together towards each other. Then, if you look at this orange lines, these ones, these are mid-oceanic ridges. This is where two plates are moving away from each other. So it is mainly the ring of fire. It has mainly this it is surrounded by the subduction like volcanic arc, but then to some extent you also have the mid-oceanic ridges present. Okay, so I hope that is clear. I'll like in the recap class I will bring when I include all the material, I think it will be easier for you. I'll prepare slides in such a way that it is helpful for you for your examination also. So that way it will be a like revision for you people. So any questions like for those who came late, I'm just uh, rushing through the topics, but then if you want me to stop and explain, you can tell me. So today we discussed about volcano. So what a volcano is, then how a magma generates. So it's basically dependent on the pressure and temperature. So when the pressure decreases, rock can melt, and if the temperature is high, so such conditions. So mainly temperature should be high, pressure should decrease, and if you have some water present, so that's how magma is generated. I'm just rushing through the topic, but if you want me to stop and explain, you can tell me. Then properties of magma, you have the viscosity, you have volatiles, and you have volume. So viscosity is basically if the magma is going to flow quickly or if the magma is going to move very slowly. So those magmas will move quickly which have less silica content, and those magma which has high silica content will move very slow, that is it has high viscosity. And if the magma has volatile content high, volatile is basically some gases or liquid whatever is present. So if the volatile content is high, that will be very that magma will result in a violent eruption, and if volatile content is less, eruption will be very quiet. Then volume of magma is also another property. So if it is high volume or if it is less, that is also a factor. In tectonic environment, so the volcanoes, they are formed largely along the plate boundaries, but an exception is the hotspot. So this I had just shown you. So this was a video just describing all the whatever I have explained. So we have the spreading zone. So this is an exception which I was talking about, the mid-Atlantic ridge in Iceland. So in all other places, the oceanic ridge is present beneath the, like inside the ocean, but this is the only place on Earth where the uh, uh, ridge is present on the surface in Iceland, mid-Atlantic ridge. Then you have the subduction zones, where when the oceanic crust subducts beneath the continental crust, so you have a series of volcanic mountains present. So this is the Cascade Range. So this plate is abducting over here. This is the continental part, and then here you have the series of volcanic mountains present. Then we have hotspots. So hotspots are an exception where you don't find the uh, uh, volcanoes in the plate boundary, but rather it is at the center. So you can say, if this is a plate, okay, so this is the hotspot. So hotspot is basically where the magma is coming from deep within the mantle. So this particular hotspot is stationary, that is not going to move. But when the plate moves above the hotspot, so what happens is, at first, let's say the volcano was formed here, then the plate moved in this direction. So this volcano will come over here and a new volcano will generate over here. So that's what in the next slide it is showing. So the example is Hawaii. So this is where the current active volcano is present. And this seamount that you are seeing over here, that is the oldest one. So as you move away from the hot plate, the mountains become older and older. So the where it is closer to the hot plate, it is younger. Then the hazards associated with volcanoes, we have the lava flows. Obviously, that is the thing which comes to our mind every time we talk about the volcanic eruption. Then we have different kinds of lava flows like Paho Ihoi and A lava flow. And then we also have the pillow lava, which when the eruption happens inside the ocean. At any point, you can stop me if you want me to explain. I'm just going through the topics which we discussed today. Yeah, yeah. Debris flow. Okay, so you're asking with respect to this volcanic eruption or the landslide part? Okay, so that I'll just explain briefly today, but tomorrow I'll be focusing entirely on the landslide part. So I can maybe show you a video or something on that. So debris flow is basically, let's say in you have a hill like this. Okay, so when this uh, for example, let's say there was a heavy rain or something, and this entire region becomes unstable and it will collapse. So when it collapses, what happens is all that material that is present over there, that will come along with this water. So it will, that debris, the debris is basically that material which has collapsed. So that with the water, when it flows, you call it as the debris flow. But even within that, we have certain varieties also, like you have this mud flow, then like in landslide, I think I have this, I prepared the slide. So we have this slow flowing, like based on the rate of flow. So if it is flowing very slowly, we call it as creep. It is, if it is flowing a bit quickly, so we have it, we call it as mud flow. So debris flow is basically a part of that. So in detail, I can tell you tomorrow, like when I'm discussing the landslide part in detail. So this is basically, the idea is that whenever a slope becomes unstable, that is whenever a landslide occurs, so all that material comes down with the water. So that is known as the debris flow. Is that okay? I'll try to incorporate some visual something tomorrow so that it is clear for you. Any question from this volcano part or from previous classes? Yeah. Sorry, I couldn't hear you. Huh? Huh? Yeah. Huh? Yes, yes. They are fertile in nature, and I think in this Maharashtra area, I don't know for sure. I think they do this cotton cultivation in such areas. I think. Yeah, exactly. Huh. Because the thing is, in India, the main thing is that that is the main, the Indian subcontinent. I'm not talking about the Andaman region, but here we don't have any active volcanoes as of now. So the regions which had volcanoes, that area is very fertile. So people are using it for cultivation. I think cotton cultivation is there. I'm not very sure. I can maybe refer it and tell you, but I think cotton cultivation is done in such soils. Okay. Huh. Somebody else was asking me something, or your mic was on? Acha, oh, okay, okay. So, where was I? Yeah, volcanic hazards में, ठीक है. So, as we just discussed, so these volcanic regions, where you have this volcanic material coming down, so that is very much rich in minerals. So that area is very fertile. So as I just said, in if these regions are not active as of now, then that area can be extensively used for agriculture and people can stay over there. That is not a risk factor. But the problem is that in regions where the volcano is still active, so the problem is people prefer to stay in areas where the soil is fertile so that they can do agriculture and flourish. But the problem is that if they stay in such areas, they are very much prone to such events. So, when people are constructing their homes or maybe anything, so they have to be very careful when they are doing it beside a volcano. So the hazards associated with volcano. So the first one is lava flow. Uh, as I said, so the lava flow, it is like basaltic flows. They are having less silica content, so they will flow very quickly. But they are not very. They don't pose that much threat. But then the andesitic lava flows, which have high silica content and high volatiles present, they can be a bit more risky. Then we have the Pahoehoe lava and Aa lava. So the Pahoehoe lava is the lava flow with smooth, billowy or ropey surfaces, while the Aa lava has rough, jagged or clinkery surface. So it's basically what is happening is when you have a let's say a bit Pahoi hoi, I think it is a bit more viscous when compared to lava. Okay, so what happens is when the lava is flowing, so it will cool down. So most of the time, what happens is the surface might cool down very quickly, but the bottom part might still be flowing a little bit. So because of which you have these ropey structures that you can see over here. So the top portion will solidify and the bottom portion will still move. So you have such ropey, textures. So that is Pahoihoi lava. Lava is when this becomes more solidified, and when the bottom part is moving, the top part will crack. So when it cracks, it will form such jagged structures, So when they walk on top of this lava material, so they can get hurt because this is very pointy in nature. So lava is a bit risky in that sense. Pahui hui is not such a big problem. Then the another category is the pillow lava. So pillow lava is formed when so this is the ocean, and you have a volcanic eruption within the ocean. So the material, when it solidifies, they will solidify in the form of small, pillow like structures. So we call it as pillow lava. So it looks like fluffed pillows. So this was a video regarding that. So if you want, I think I'll be uploading the recording so you can watch from there, or the slides also I'll be uploading so you can go through that. Then you have the pyroclastic flows, which are very, very dangerous. So if you look at this diagram also, you can see, right? So this thick smoke is there, and you can see how fast they move very quickly. So that is what is written over here. So the speed of like 50 to more than 200 kilometer, that is how it moves. So if you had seen the that Pompeii video, so there this pyroclastic material has significantly resulted in the cause of like people losing their lives and all. So they move very quickly. I think this video I'll just play it one more time. Like those who have already seen, I'm sorry, but I'm just showing it for the people who have joined late, just for you to understand how dangerous this is. So you can see, right, a person running can get engulfed by this pyroclastic material very quickly, and they are like 50 to 200 kilometer per hour is like very high. So it can even overtake a car, for that matter. See how quickly it is coming down. So that was a video regarding the pyroclastic flow. So you can see how quickly it moves and how lethal it is. So whenever you think about a volcanic eruption, the image that comes to your mind is the flowing lava. But it's not just that. Even the ash and the pyroclastic material, all that will create problems for this life and property, which is why we call it as volcanic hazard. Sen, ash is the mixture of rock, mineral, and glass particles expelled from the volcano. So they are very small, but they are very dangerous. Like when you inhale, if people have respiratory problems, then that can aggravate the situation and create more problems. So, and at the same time, I have shown you an image also. So the volcanic ash is accumulating on the rooftop. So if it accumulates so much, then it will become heavy and it will collapse down. So that way it will damage the structures. So health wise, inhaling the volcanic ash is not good, and property wise, if you see, this can result in collapse of structures. Then you have the volcanic mud flow. So volcanic mud flow is when this ash combines with water. So that is another volcanic hazard associated with the eruption. So here you can see this example I had shown. So here there is a person who is like around 6 feet tall, and these trees have the mud flow lines present. So you can see almost like 12 to like more than that feet tall mud flow has happened. So that way anything in its path would have been engulfed by the mud flow. Then this was just to show you the mud flow path. So like in 1995 this area was not very much populated, like isolated people were there. But then by 2009 people have completely accumulated this region, because this area will definitely have fertile material because the volcano has erupted and brought such material. That's why you're seeing this farmland and everything. But the problem is, maybe the volcano has not erupted in like these many years, but that doesn't guarantee that the volcano will not erupt. But in if in in future it erupts, this will be the mud flow path down the valley and all this area will be covered. So these people will have to take precaution regarding that, like in such events, to move away from the area and all. So the authorities and all those related to that will have to keep monitoring this volcano. Then another hazardous factor is the poisonous gases. So carbon dioxide, sulfur dioxide, which and eventually sulfuric acid can form. So all these are poisonous in nature, and if you inhale it, that will definitely result in death. So an example of that is this. So you have this Lake Neos. So this I had already explained, but I'm just telling you. So if you have a mountain, volcanic mountain like this, and its top portion collapsed, okay. So when it collapses, it will become something like this. So this is a crater, and then later on, this crater will be filled with water, so it becomes a lake. So that is what this Lake Neos is. So what happened is, this Lake Neos had significant carbon dioxide present in it because of this volcano. And what happened is that it overflowed along a waterfall, and basically all the cattle and people nearby in that area suffocated because of that excess of carbon dioxide coming. So, if you are asked about the hazards associated with volcanoes, you have to talk about the poisonous gases, then you have to talk about the mud flow, then the volcanic ash, then the pyroclastic flows, and basically the lava flow. So, these are all the hazards associated with a volcanic eruption. Then this was what I was telling you, like just like CO2, you also have sulfur dioxide. Okay, so what happens is, when the sulfur dioxide gas combines with oxygen, it will become sulfur trioxide, and when it combines with water, it will become sulfuric acid. And those of you who are familiar with this term, sulfuric acid is very dangerous, right? So that way also it can cause problems. Then, as I had already mentioned, when these gases or particles go into the atmosphere, they will block the sunlight, which eventually results in a cool climate, which is not very good also. Like, you might think, okay, sun is not there, it is cool, it is better, but that's not the case. uh, I think I had shown an example also where almost a whole year, that area experienced a very cool condition. So that's also not good. So, can volcanic eruptions be predicted? So, that is basically just like the earthquake, like scientists can do long-term forecast. So, if they study the past volcanic eruption in that area, that is basically the paleovolcanology. So, if they study the past volcanic eruption, they can establish a trend. So, if in one area the eruption, let's say, took place in 1995. Okay, first one eruption, they noticed that it happened in 1995. Then in let's say 2005, another eruption happened. So then 2015 another eruption happened. So they have this data, so they can see that there is a decade interval, right, a 10-year interval. So then they can say that maybe you can expect an eruption in 2025. I'm just saying it for your understanding, but you have to also understand that there are volcanoes which appear to be inactive, but because they have not erupted for, like, say, thousands of years, but that does not guarantee you that that is an inactive volcano. Definitely, not definitely, but there is a possibility that the volcano can become active in the future. So just like earthquakes, volcanoes also, you cannot be very certain, but then to some extent, scientists can give you a warning. Then earthquake tremors, like whenever, like some examples, precursors of volcanic eruption is earthquake tremors. Sometimes small scale earthquakes can happen, or the surface of the volcanic mountain can experience some kind of bulging. Okay, so initially it was like this bulging is coming means this interior has become active. So such things, or changes in the gas concentration, so they will continuously monitor the gas concentration in this area, and if the concentration has increased, that is indicative of the fact that this region is becoming more active. So this is an example, like they kept, before the eruption, they kept a tilt meter over here, so to monitor the difference. And then when the magma started rising, this flank became bulged. So the tilt meter also recorded that. So when they looked at the data, they could see that whenever that bulge was recorded, uh, a volcanic eruption has happened. So because of that, people keep monitoring this bulge. So that is what I have discussed in today's class. So I just quickly did a recap, but if you have any questions, you can ask me. And it's not necessary that for like, you have to only ask about volcano part. Even the previous discussions you can ask me. I'll definitely do a recap of the entire natural hazards course on, I think, March 19th, before your exam, so it will be easier for you. So I hope to find all of you during that session. And just a reminder that we will be having a session tomorrow to compensate for last week. Last week I couldn't take it, so tomorrow we'll have another session where I'll be discussing about landslides. So, do you have any questions for me? Okay. Thank you so much for listening to me. And as I said, feel free to ask me anytime. Uh, so, if you don't have any questions, then we can end today's session. You can leave the meeting, like if you don't have any questions.